Thank you very much for your attention and for being here. And it's a great pleasure to introduce Dr. Song, and who came from New York. And she was had some issue with her flight and wasn't feeling entirely comfortable, but she's fully recovered as far as I can see. And welcome to be here. And thank you for giving us this talk. And so we rarely have people coming from industry to give us talks. And so this is a great opportunity for us to learn and the people from industry. And Dr. Song is actually a leader in the industry that is very, very promising. We know that wind energy is a very important renewable energy sources. And the offshore wind energy is another frontier of wind energy that is going forward in the next 40 years. That's where the wind energy is going to get the largest bloom in this field. And Dr. Song is a leader in the GE, which is the biggest player, one of the biggest players in the wind turbine field, and to lead the research in the offshore wind energy and help us to develop the new directions moving forward. And it's also interesting to know she had a background actually in optical engineering, kind of overlaps with a lot of things with what I do. And also you have done some postdoc work on the biomedical engineering. That's very interesting. So I'm very curious to see how she was able to make a transition from biomedical engineering to study offshore wind turbines. With no further ado, now the floor is yours.
Thank you very much. Can you guys hear me okay? Yeah, although Dr. Hong said I'm fully recovered, you may still hear I had a cold, so my voice may sound weird. Sorry about that. So when I met with Dr. Hong this morning, he mentioned this is the most slowest year for Minnesota. One of them, okay. Yeah. From where I came from, upstate New York, this is the most warmest year for upstate New York. So you can see the global warming is changing the weather patterns this year, in the past, and in the future to worse. So that's why in the Paris Climate Summit, to reach the climate goal of less than 1.5 degree global warming by 2050, we have to reach net zero emission. That's why renewable energy is so important, and the offshore wind is the frontier of the renewable energy. So my name is Guiju Song, coming from GE. I would like to share the industrial perspective in terms of the offshore wind, particularly my research interest in the offshore wind operation and maintenance. You may have paid attention to GE. There's a lot of recent news, or you never heard about the GE. So I'm thinking before I deep dive into the offshore wind topic, let's talk about the GE a little bit. After that, I will share our view about today Ashore vision. That's really about how GE think about the future offshore wind operation and maintenance, how we can lower the cost of doing this OM, and in turn to reduce the levelized cost of energy. So I will share two government-funded projects as a case study in terms of driving the today Ashore vision. In the last, I will give a summary in time in terms of our takeaway for this research field. So this is a long history about the GE, starting from 1879. Thomas Edison invented the first electric lamp. After that, we are in the forefront of all kinds of inventions and innovations. For example, in 1896, GE invented the first X-ray machine. Later on, we invented the first US jet engine. And then if you look at the bottom, coming to a little bit of recent years, GE started to get into the wind energy, offshore wind, additive, and so on and so forth. So all of this cutting edge research. So from the 130 years of history, now GE's power generation machine is generating 1/3 of the world's electricity. And our aircraft engine is powering 2/3 of the commercial airplanes. Every 10 seconds, there's one airplane powered by GE aero engine take off. From the healthcare perspective, we are curing 16,000 patients every minute by scanning, imaging their body, and be able to diagnose the health. So this is a long history. Come to last year, GE has announced to be split to 3 companies. Look at these 3 numbers. So now the new GE will be split to 3 companies. One is called GE Healthcare, focusing on human beings' well-being, health. The second one is GE Aerospace, focus on the aircraft engine, aerospace. The third one is the energy. That includes traditional gas power, wind energy, grid, and also hydro. So the sub-business I belong to is the GE energy segment. Our new name is GE Vernova. So the research center I come from also were split to 3 different advanced research center. One goes to GE Aerospace, another one goes to GE Healthcare, the third one goes to the GE Vernova. I'm from the GE Vernova Research Center, focused on research and technology development for the energy transition. Hope this is clear to you. Okay, so now let's talk about why offshore wind is so important. So I mentioned the 1.5 degree of global warming. That means 56 gigatons of greenhouse emission needs to be reduced. This is a humongous of a goal. So in order to do that, we have to transform how we produce, means energy generation, how we consume, means how we use the energy, how we move around, means how we change our transportation through electric vehicle, through electric airplane, and so on and so forth. So as you all know, 70% of the surface of our planet is ocean, right? So ocean should play a significant role to achieve this gas emission reduction goals. Among this ocean-based renewable energy solution, offshore wind, come here, yep. Okay, here it is. So ocean-based renewable energy represents 45% of this emission reduction potential in the ocean. Among the ocean-based renewable energy, offshore wind can contribute significant of that, and also comparing to tide and other ocean-based renewable energy, offshore wind is the mostly advanced from a commercial perspective, and the increase rate is 30% annually. So GE is in the frontier of the offshore wind technology. You can see this picture is from the Block Island, the first US offshore wind farm in Rhode Island. There's a 6 megawatts wind turbine being installed back to 2016 and still in operation. This is the second commercial wind farm in Germany. We call it Merkur. So in the Merkur wind farm, there's 66 wind turbines installed over 18 square miles. Technology advancement and research never stops. Back to 29, GE launched this 100X prototype, which is 12 megawatts offshore wind turbine. It's the largest one in the field. I mean, you may hear the news announcement, there's a 15, there's a 17, even 20 megawatts offshore turbine, but it's on paper, it's a paper design. So this one is real. It's in Rotterdam of the Netherlands in operation, connected with the grid. Just imagine how big this wind turbine is. There's some like a comparison with the Eiffel Tower and also the building in the New York City. So the blade length is 107 meters and the rotor diameter is 220 meters. The tower is 260 meters tall. It's a gigantic machine, right? But keep in mind, one rotation of this turbine can power one US household for 2 days. So such a powerful machine, you may think, okay, it must be very expensive to operate and maintain. Yes, you are correct. So here's some of the pictures, facts about the offshore wind OM. All the pictures are real, right? So in order to do maintenance, you may lift someone with the helicopter to this helipad. So this person, this technician, can do some inspection and repair jobs for the turbine. This guy is on the turbine blade, just on top of that, with, of course, with the safety tether to do the repair. And this is inside the nacelle. This guy is inside a turbine. I'm not sure what he's doing, but he's doing something there. So this kind of boats is very typical. Maybe the diameter is more than 0.5 meters. For the first 2 years, you need to tighten these boats every 6 months. After that 2 years, you feel comfortable of the safety, of the reliability. You may just go there, inspect, and tighten it once a year. It's a huge cost. This guy hanging there, do something for the tower. And of course, this foundation and these cables are underwater. The inspection and the maintenance will cost even more. And all these activities firstly impose danger to our trained technician, to human life. On the other hand, it means a huge amount of cost. It, of course, dramatically increase your levelized cost of energy. So that's why we launched the Stay Offshore vision. Before I talk about the Stay Offshore vision, I want to give you just a little bit of ground in terms of what we do exactly for this maintenance, right? So you may hear from onshore practice, the OM cost contributed to about 20% of the levelized cost of energy. For offshore wind, this number is 35%. For normal practice, there's a planned maintenance and unplanned maintenance. For planned maintenance, you do it once a year or twice a year. During this maintenance, you may need to do the regular inspection and the lubrication, maybe boat torquing. I showed a picture a moment ago. It's really tighten the boat. And also, you may do some like inspection, for example, the blade health and so on and so forth. So the Stay Ashore vision is really about improve the productivity of this planned maintenance. You just touch the components as necessary. Your time is meaningful instead of just do it based upon calendar according to your manual. The second type of maintenance is unplanned maintenance. That means you operate your turbine remotely somewhere in Atlanta, but somehow your failure stop operating, you lose production. So you need to send someone over there. Renting the boat is hugely expensive. So we want to avoid this unplanned maintenance through some remote monitoring, AI digital twin, of course. In the future, you want to reduce the human-dependent operation and maintenance. You want to utilize robots underwater vehicle to perform these tasks. So what is the Stay Ashore vision? In the Stay Ashore vision, we include 4 elements of technology. The first one is connect. In order to understand the health condition of your turbine, your wind farm, you really need to deploy a sensor to monitor every component, every subsystem, the entire turbine, so you can have data. Transmit the data to a remote site. So the data is accessible from anywhere around the world. That's the first element. The second element is analyze. Once you have the data, what can you do, right? So luckily, there's a AI machine learning advancement. There's a digital twin model that has been applied in other industries, such as conventional energy generation, such as the aerospace, and even transportation, right? So we want to leverage the technology advancement in other industry for offshore wind operation and maintenance. That's a second element. The third one is managing. You have the data, you have the model uncover the hidden insights, tell you the history, the present and the future of your assets. Then what do you do? So there's a decision support kind of activities. We call it manage. The last one is optimize. One option is, okay, my AI model tells me this blade will fail in 3 months. Should we do it in 3 months? Or should I do it in next 2 months? Or I can run the blade a little bit harder, although I can afford the reliability price. But because it's a summer season, the energy price is high. Economically, I can make more money, although I sacrifice the reliability of the blade. So all these factors need to be considered, optimized through a model. That's the last element about optimization. In the next, maybe we have 20 minutes or 30 minutes, I will give 2 examples of these projects. One is about the Connect, how we develop an autonomous inspection vessel to acquire data to inspect the turbine. The second project is about utilizing AI machine learning so we can estimate the health state of the turbine blade and predict what will happen in the future. Hope all the insights will help us to enable condition-based maintenance. So these 2 projects are funded by the Department of Energy, National Offshore Wind Research and Development Consortium, and also LYSERDA. LYSERDA stands for New York State Energy Research and Development Authority. So I want to acknowledge their funding support and also their guidance to the project direction and the program management. But by no means, the topics and the conclusions I have represent any point of view from DOE, now RDC, or NYSERDA. So the first project is about the autonomous inspection vessel for offshore wind. This project was started October of last year, so it's still ongoing. The goal of this project is really to utilize autonomous vessel to help us take data, acquire data from the turbine instead of sending human or adding new sensors. Although I mentioned in the still show vision, you want to monitor every component, every turbine, but adding one single sensor will add a cost to the entire capital investment. And in the meantime, once you have one more sensor, the sensor failure may contribute to another failure mode to you. So ideally, you don't want to really add that many sensors on the turbine. Enough is enough. But what can we do? We can utilize this very mobile autonomous vessel to acquire data to do the inspection. So this project goal is really to develop a solution utilizing this autonomous vessel carrying different kinds of imaging modalities to acquire data from the blade. So you can see through this kind of method, we can reduce the inspection cost comparing to human being. Of course, we can improve the EHS, reduce the safety risk, reduce the downtime, because this little guy can do the inspection in real time when your turbine is rotating. You don't need to stop that. Just a fun fact. Like a drone is used for offshore wind turbine inspection today. But in order for drone to take a high quality image, you need to stop the turbine. So the blade is kind of idling over there. So this one you can do in real time. No need to stop the turbine. That's from the downtime perspective. Another perspective is about the repair cost. Although this little guy only doing inspection, but because we can do it so often, so you understand your asset condition in real time instead of inspecting every 6 months, right? You have like a very large interval. Once we know better about the blade health, we can do the repair earlier. Early repair means less cost and also extension of the life of the blades. That's another advantage. So regarding the modality we have in this project, the first one is the burst photography. So I'm not sure how many of you are really involved in the wind maintenance. So burst photography is like a typical way for onshore wind. Someone carry a burst photography kind of imaging device, take a snapshot for wind turbine blades. And in today's practice, this technician need to go to the hotel, check image one by one, and get rid of those useless image and then highlight the defects. So in our method, we will adopt the hardware from this onshore inspection to capture the blade surface imaging. It will help us to identify any defects. The second type of image.
First, sorry for interruption.
Sure.
The first photography is like the strobe lighting, you know.
Yeah, yes. Yeah, exactly. Yeah. So by the way, feel free to ask a question at any time. I talk like a non-stop. So please interrupt me for any questions. So the second modality is thermal imaging. The thermal imaging can help us to detect the defects from the structural perspective. For example, some small crack, some like underneath defects such as material delamination and so on and so forth. The third modality is LiDAR. So LiDAR can help us to monitor the blade aeroelastic behavior and also help us to check the aerodynamic performance. All the modality will be housed on this autonomous vessel. Every time this vessel can be launched from the shore, go to the wind farm site and acquire data automatically. All this data will be transmitted through some like a satellite or like a Starlink type of communication protocol to the remote control room. So that's about the nutshell of this project. As I mentioned, this is 6 months of this project. Our goal is to integrate a system described a moment ago, do the field test in the Block Island wind farm. Remember the picture I showed in my second slide? So we will do that field test in summer of this year. Hopefully from that field test, we will have a better understanding in terms of the capability of the vessel, capability of the imaging modality, and also the data quality. So good for this project.
Is this autonomous vehicle travel on a designated path, or is somebody's without remote control?
Yeah, so for this particular one, someone need to control in their room. Their room is in Ireland. So yeah. So my next project is enabling prognostics and the start of the offshore wind. Just 10 minutes ago, I mentioned all this AI, machine learning, digital twin have been applied to other industry. Naturally, we want to apply for the offshore wind, but there's some issues because offshore wind has such a young history. Even for the Block Island, it's only 6 years in operation. In order to apply AI, machine learning, digital twin, you need to have a huge amount of data. You need to have failure modes and failure events, right? That's a foundation for building and using machine learning models. So for offshore wind, we don't have that many data, so that much data. So that's one of the challenges. This project is really to build a technology framework to address the challenge I just mentioned. Why we want to do that? So I mentioned the 35% of LCOE impact early on. If we do condition-based maintenance for all the components, hope we can address a significant portion of that 35% of LCOE. That's one. Because there's so many different components, there's so many different failure modes. You don't want to boil the ocean at once. What we did is identify one of the critical failure modes, leading edge erosion. For proof of concept, after we prove this technology framework can work, we can easily apply and leverage for other components and other failure modes. So why we choose leading edge erosion? Leading edge erosion is really about the blade surface is eroded due to the rainfalls and also some other like a salty environment. Since there's a erosion, the aerodynamics will be changed, and then that will impact the annual energy production. On average, this kind of leading edge erosion, if not repaired, will cause 5% of the AEP loss. I mean, Sandia has a publication. They were even talking about the 25% of AEP loss. That's huge. So we utilize leading edge erosion as our first use case for proof of concept. What I also want to mention here is no sensor. Remember what I mentioned a moment ago? No additional sensor. We just want to develop a software-based solution, so it's cost-free. On my right side, that's the two core challenges in this type of application. Otherwise, the Department of Energy or now RDC will say, hey, it's a GE problem. You go there, invest, and solve the problem. But it's not a GE problem only. So it's an industrial common problem because the data sparsity. I mentioned a moment ago, not enough history, no failure data. So that's industrial-wide challenge. The second one is model validation and calibration for our confident deployment. There's so many publications, there's so many kind of research going on talking about under the data sparsity situation, how can we still utilize the machine learning, AI, to enable this condition-based mechanism. Okay, that's fine. But in order to deploy the turbine, in order to deploy this model to a real turbine, you need to have the calibration and validation done. Otherwise, it's impossible to convince any of the wind farm, wind operator to adopt your model. So that's the second challenge. In our project, we embrace a 4 steps approach to tackle these two scientific challenges. The first step is about data generation. We have lots of data, which is good turbine operation. We want to simulate some of the failure events so we can utilize the model. That's step number 1. Step number 2, of course, is a model building. There's so many different machine learning approach. You still need to do a fair amount of research to identify one optimal model to give you the good performance. The third one is model calibration. And the last piece is remaining useful life prediction. Besides knowing the today's state, you want to predict what will happen in the future. Okay, so before I jump to step-by-step progress and results, I want to share our approach first. So this is just to give you what we're doing, how we do this. Our approach includes 2 phases. The first phase is generating data. In short, generating data means we utilize high fidelity physics model to generate simulation data. This simulation data represents how the turbine will behave under different failure modes. So this high fidelity physics model is a turbine design model. In order to do the data simulation, we laid up a design of experiments. This design of experiments includes a different combination of wind condition, environment condition, and the roughness levels. Now you may wonder why we are talking about roughness level. We're talking about leading edge erosion, right? So leading edge erosion really changes the surface roughness of the blade. Because for this high fidelity physics model, it cannot take in or ingest leading edge erosion. It can take in roughness levels change. So we use roughness level to represent the leading edge erosion. Hope this is clear. Through this design of experiment, we can generate a bunch of outputs. These outputs are really the operational variables for a particular wind turbine. So the
roughness, you can impose all kind of surface, right?
Yes.
Then you have to estimate the lift coefficient, right?
Yes.
So how is that done?
Exactly. Yes, that's a right question. This roughness level means different drag and lift coefficients, and the high physics model only can take the drag lift coefficients. So mapping between the roughness and the 2 coefficients are done in the tunnel test.
So we done.
Yes, yes. Because we have the real wind turbine blade design, the LM team, they produce this turbine, they did all the tunnel tests, so they provide their profile to us. Yeah.
So you measure directly the
Exactly, yes, 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 yeah. Thank you. That finished the data simulation step. The second step is, okay, now we have data, let's build a model. The goal for build a model is, as I mentioned, there's no additional sensor. We only have data available today. So let's say the data available today, either from the direct sensor measurements or from the control estimation, or some of the features derived from the sensor measurements. Utilize all this as my model inputs. Can we estimate the surface roughness? So that's basically a problem statement for the model building phase. So in this case, we also consider wind condition and the environmental condition, because these are some critical factors impacting the blade, the turbine health. Now let me share some of the results. The step number 1, in our case, we designed 17 different roughness levels, because the wind turbine blade on the tip side, the rotation speed is much higher. So the leading edge erosion or roughness always happen in the tip side. In our project, we increase the roughness level from like a 2/3 from the root. Think about it, here's the blade root. This is a 2/3 from the root, and this is 1/3 from the tip. So the roughness increase always happen in the last 2/3, in the 1/3 to the tip. And the wind condition include wind speed, shear, and turbulence intensity. Environmental conditions, normally we're talking about air density. So all these are the inputs to my model, and I run the DOE I just mentioned. We generate 11,000 of simulation data sets. And from the 11,000 simulation data sets, there's about 53 operation variables. All these variables can be measured. All these variables can be acquired from existing SCADA data or the controller of the wind turbine. That's the first step. The second step is about the model building. So from these 53 variables, are all of them significant for my model building? The answer is no. So we did some like significant analysis, ranking the importance of each of the variable. In the end, we selected a few for our model building. So from model building perspective, as I mentioned earlier on, you really want to take some of the available operation variables as your inputs, build this transfer function. So at any given time, if you apply your SCADA data to this model, I can tell you, hey, exactly at this given moment, what is your roughness level? So that's the purpose of building this roughness model. HIE stands for Health Index Estimation. We tried a different machine learning approach, include extreme learning machine, random forest, lasso, and so on and so forth. Of course, this is a typical machine learning model building process. You divide your data to 80% for training and 20% for testing, and to validate your model performance. So you can see from this study, we selected electric extreme learning machine as the optimal modeling approach for us. So the third step is the calibration. As I mentioned, in order to have that confidence to deploy your model, you have to validate, calibrate the model. We come up with 2 different calibration method and strategy based upon the real scenario. In real scenario, the first type is really about the difference between the simulation space and the field space. So this is the 100X prototype, the 12 megawatts prototype in Rotterdam of the Netherlands. So we got a field data from this turbine. We compare against our simulation space. We see the difference between those. So that means, okay, from the simulation, we know the design specification of this turbine, but in reality, in the Rotterdam, seems the environmental condition is more toward a little bit another end. So the calibration approach to deal with this difference is to re-simulate. We know the reality. Let's just add a little bit more DOE to our simulation so we can cover a broader space. That's the first calibration method. The second calibration method is really about dealing beyond the simulation. So I mentioned the Haliade X is the 12 megawatts by design. But in order to, everyone is competing to like a higher capacity. So this 12 megawatts prototype has been operated at 13, 14 megawatts and a different time frame to get the certificate. Once you get the certificate, you can start to sell these turbines to customer. So GE run this turbine at 13, 14 megawatts, got the certification, and we were able to sell this 13, 14 megawatts turbine to UK, the Docker Bank, offshore wind farm, Empire Wind. Empire Wind is New York State. Yeah. And another one from Massachusetts. So that means, okay, your model built from 12 megawatts simulation data may not be able to apply it for this 13, 14 megawatts. It's the same turbine, just operating in a different regime. So how should we do that? Oh, luckily, because you run this turbine in 13, 14 megawatts, although it's within a very short period of window, in this case, it's only like 2-3 months, but you still have this field data. So the calibration approach here is to incorporate real world data into your model building. You update your model so the model can reflect the real world operation and condition. So that's the second calibration approach in our project. The flow chart here really highlights the two calibration approach I mentioned. So on the left side, we can see how, okay, the turbines are operating at 12 megawatts, but we have difference between simulation space and the real world. Let's just do another simulation, expand our simulation space to include this field condition. So we got a new set of DOE and then build a model based upon these new data sets. On the right side, that's another scenario I mentioned. We have 14 megawatts data from April of 2020. So let's include some of those data into the model updating process. So we have a new model, and this new model will work for this 14 megawatts of operation. So that's just like a very simple flow chart in terms of how to adapt a model built from simulation data to the real world. So the bottom two charts are the comparison of the model performance before calibration and after calibration. Because the turbine is so new, actually there's no real like a very rough situation yet. We treat the turbine as clean. Clean means in our case 12.5%. So that means all the prediction results should be clean. But before the calibration, you can see some of the cases, a huge number of cases are predicted as very rough. I'm sorry about the black font, you may not be able to read it. So this is like 120 here percent rough. After the calibration and all this error prediction was corrected, so it's back to clean state. Okay, I hope this is clear to you so far.
Just curious, why don't you market this as a 40 megawatts wind turbine? Why don't you still market it as 12 megawatts?
We market it as 12, 13, 14, 15 right now.
Oh, okay.
Yes, yeah. As I said, 14 was sold to Docker Bank, Empire Wind, yeah, in the US, Docker Bank in the UK, yeah. For 12 was the original design. Okay. Yeah. So the fourth step is about the future. Of course, there's a huge amount of argument in terms of what is the remaining useful life, because you really don't know what's your end of your life, right? So it's difficult to say what's the remaining useful life. But since that's the topic everyone is talking about, it will give you some indication about the future degradation. So we still conducted this task. What we did is leveraging the rain erosion testing data from the lab. I mentioned in the beginning, this raindrops, volume, and also the environmental condition contribute to the blade roughness change or leading edge erosion. So GE has a facility to do this lab-based rain erosion test. You can see the machine over here is rotating, and we have a piece of this airfoil underneath. So there's lots of syringes on top of this machine, and we can control the water drop speed, volume, and other parameters. So after accumulation of accumulation of this rain impingement, and we observe some like erosion, which is equivalent to roughness. So if you're interested in this lab-based rain erosion test, there's a YouTube video you can watch. I have a link over here. So this is the data, only data we can leverage. Then how we build the remaining useful life. So from this rain erosion lab test, we know a curve. This curve, the y-axis is the blade roughness. The x-axis is the total water volume, or we can call it a precipitation. So that's the curve available from the lab test. So in order to translate this to a real situation, luckily we found the weather data across a few countries in the UK. Remember, this turbine was installed in the Rotterdam of the Netherlands, right? So there's more than 20 weather stations across the European country. The Rotterdam, by a good accident, there was one weather station. We were able to download that open source weather data for Rotterdam. So we know in the past 20, 30 years, every month, what's the total like precipitation for that location. So by leveraging that, we translate this lab-based rain erosion test to the Rotterdam situation. So we got a few data points. For example, we know like the turbine was installed in like 2019, and then after 1 month, 2 months, 3 months, 5, and 7 months, each month we know how much rain in this Rotterdam, and when we correlate to the lab test, and we are able to figure out, okay, the roughness for this month should be like 25%, and then by 11 months should be, I think here's like 40% or a little bit less. So we got a few data points from the 6 months of this turbine. And of course, once you get this a few data points, you can do like a linear or non-linear regression, and then build a curve that represents your trend. And once you have that regression, you can project to the future. So in this case, the remaining useful life is not a life to failure because it's a leading erosion that barely can cause a turbine blade failure. It causes the loss of the annual energy production. So the definition for the remaining useful life is really defined by the user. How much loss they can tolerate. I mean, it depends on the operator. Some operator may think, okay, 1% of AEP loss is my maximum. If I reach 1% of AEP loss, I must to do some repair. Or some operator said 0.5% is my threshold, or 1.5%. So that's really about the user-defined threshold. So just for like a demonstration, let's say 70% is the tolerance, is the threshold. So based upon the 6 data points we project, we build the model and the 11 months, and we project to the future, and we said, okay, in the 19 months, we will obtain this kind of 70% of roughness, and in that time you need to do some repair. Then the remaining useful life is really from here to here. That's about 8 months. But in reality, we know this blade leading edge should last 22 months. So that means you have some of the error. Once you get more data you get the data here, here. You're closer to the end of the life. Your regression is more accurate, and your prediction error should be much smaller. So in order to validate whether this remaining useful life model really works, we also want to get more data at a later stage, make sure the error is converged when we get closer to the real end of this life. Okay, so that's the step number 4. This is 18 months project we completed last December, and this year we got some Guiju internal funding to bring this forward. Because for this DOE and National Offshore Wind RDC funding, the end goal was TRL 4 and 5. Means you prove the concept, you develop the technology, validate with lab data, validate or with the field relevant data. So after the technology readiness level 5, you want to bring to a production, there's still more work to do. That will involve more like calibration, validation, and also deal with all other uncertainties. So we got some Guiju internal funding to bring this forward. That's what we are working on right now. So I just want to give you a summary in terms of what we got, the key takeaways from this project. The first one is I mentioned the grand challenge for building this AI machine learning model from the start of the assets, from the new assets. So what is the key ingredients here for the success? The first part is from the model building perspective. Data is a challenge. If you go to any of this offshore wind related conference, people always say, oh, we want more data, share your data. Why you guys are so kind of enclosed, right? So my point of view is, I mean, no one has the data. Even for the operator, the OEM, you only have like a limited amount of data, which is good data. In order to build a model, you need the bad data, which is the failure data. So try everything to get the data. Either like our case, from the simulation or from lab testing, just leverage any data you can get access. That's one. Second is, in order for model to be successful, you need to cover a wide range of operating modes. As we did, well, we run the simulation and consider the difference between simulation space and the real field, and then rerun the whole simulation. That's that. The last one is the domain physics knowledge. So I think this is very important. If you still remember the two phases of chart, on the top, I mentioned this 11,000 of DOE simulation. The outputs is 53 operation variables, but we didn't use 53 operation variable. Why? Because for this 100x 12 megawatts, you may have the 53 operation variables. If you go to somebody else's turbine, they may not have that 53 operational variables, right? So in order to get the minimum necessary, we utilize some domain knowledge to reduce the total operation variables we need to use. In the machine learning language, we call this feature selection. So there's lots of domain knowledge and physics knowledge behind for us to eventually save the 53 variables to that selection until we get a few. In our case, it's like a 7. For the 12 operation, 10 for the 14 operation regimes. So that's some takeaway from the model building perspective. From deploying perspective, I keep saying, hey, validation is important. Okay, that's good. We're done with the calibration. But for the operator to accept this model, you need to have a way to explain how this model works. I think model explainability or interpretability is a very hard research topic today in order to deploy any machine learning model. The next one is continuous learning. I mentioned we have a continuing funding this year to bring this to real world. The hope is to get more data after the deployment. This model should be a live model. you keep updating it once you get more data. So that's very important for the deployment phase. Again, after you deploy that, you keep doing calibration and updates in a periodic phases. So that's about the key takeaway for this particular project. But as I said, the goal is to prove the concept for this technology framework instead of just focus on one user case. So we believe this framework can be applied to other renewable energy or even energy transition related industry or technology. Of course, today we have proved that for offshore wind blades. We believe this technology can be applied for other wind turbine components. And my colleague has another project funded by APAE, which is apply similar framework to the nuclear power plant. And future opportunity include the nacelle drivetrain tower for offshore wind. And you guys know floating offshore wind is such a hot, sexy topic. Of course, right now it's talking about supply chain challenge, design, reliability of floating offshore wind. But one day, very soon, the operation and the maintenance for floating offshore wind will come to the picture. So let's prepare for that. This type of technology will definitely be applied for the floating offshore wind OM. And of course, the transmission grid is a natural extension for this type of technology when there's not much data available. So in conclusion, enabling this offshore wind operation and maintenance automation is the future for offshore wind cost reduction and risk mitigation. So thank you very much. Any questions, welcome.
Thank you very much for the excellent talk. Let's see if there are questions from the audience. Go ahead, Amy. Oh, yeah, sorry about that.
This might be a basic question, but how different are the failure modes between offshore turbines and those on land?
So actually, they are the same. Maybe just a different severity level. So as I said, the data sparsity is challenging. In the beginning, we don't know how to do it. So we were even thinking about for onshore wind turbine blade, there's so many inspection. Can we analyze this inspection images just to get an understanding about the leading-edge erosion, how the failure modes propagate? Maybe do some like a transfer learning type of technology, and then offshore wind can have a model. Of course, in the end, we didn't go that way because even for onshore leading edge erosion, you have a bunch of images, but it's unstructured data, uncurated data. It's a bunch of images. You even need another 1 million of a research fund to figure out what that data means for you. So failure modes wise is very similar, although the environment is different, but it will happen in both onshore and offshore. Just the severity level and the damage level is different.
Great, thanks.
Thank you. Thank you. Interesting. Yes. So you talk about roughness as a single parameter, but I'm sure that everybody dealing with roughness will know that there's not one parameter. So how do you classify roughness, and what is the key parameter that you use, or the list of parameters that you use to guide your experimentation and everything? Because I'm sure that it's not sand grain roughness. I mean, you have a blade spanning at probably 100 to 100 meters per second, somewhere there, and hitting whatever is, different rains and different salinity, all kind of issues. So I'm sure that the roughness will change, and even the anisotropy of the roughness along the bundle layer development. So
yeah.
And I don't know, that probably says some proprietary things, but I was just curious about it.
Sure, that's a very good question. So firstly, as I mentioned, we have an ongoing project this year. That's exactly to map the roughness to some of the leading edge erosion you can observe from the field. As you mentioned, maybe the real linear erosion and some parameter can change your roughness, right? So in the end of the day, roughness means nothing. If I tell you this is 75%, what can you do? You cannot do anything. So you have to map that roughness to the observable phenomenon from the field. In our case, is the drone inspection image. The drone inspection image show you, okay, in the last 1/3 of a section of my blade, I have some linear erosion here, some missing patch here, some over there. So location-wise and size-wise, we want to build a transfer function to map this roughness changes to that observable linear erosion. And in the meantime, in the real maintenance, the decision is not made because we know here's like a 3 millimeter of linear erosion here, 2 millimeter over there. They categorize the linear erosion failure to different category. We call it Cat 1, Cat 2, Cat 5. So the decision is really based upon is a Cat 3 or Cat 5. So our goal of this year's project is map the roughness level from our model to this Cat 1, 2, 3, 4, 5. So we can have some like a decision support insights. That piece is missing in the government funded project. So in the end of the day, the absolute value of the roughness does not mean anything. Maybe that answers some of your question.
Yeah. So basically, when you do the testing, you reproduce the same roughness that you get from the drone.
Yeah.
So it's a 1-to-1 scale. You don't need to model the roughness. You
Yeah,
just
yeah.
go for it.
Yeah, and then what's in between, like the Cat 2 and the Cat 3, what's in between doesn't matter because anyway, we don't use that for maintenance decision. We only need to know it's the Cat 3 or 2. So.
Okay, thank you.
Thank you for nice and energetic talk.
Thank you.
Yeah, I have a question. Do you have any concerns regarding the negative environmental impact of offshore turbines on marine ecosystems, for example?
Yes. So this morning, I think I spoke with these two gentlemen over there. So actually, the California Energy Commission launched a funding opportunity back to October of last year. It's really about the studying of wildlife impact from the floating offshore wind. So we participated in that proposal call. Actually, we were selected. So in the future, we will do this type of research and see how this, of course, the CEC opportunities for floating offshore wind. For the fixed bottom offshore wind is similar. Let's understand how the presence of this offshore wind turbine will impact the wildlife, maybe in a negative way or in a positive way. In a positive way means, oh, the bird sees the turbine, let's fly away. So that's what I meant.
Well, I'm afraid there is no positive way, but in any case, we know that sound that is generated, there are many publications about sound impact on birds. But for example, if I'm looking at your turbines, definitely flow field in the proximity of these turbine farms will be changed. In other words, according to the last Glasgow Agreement on climate change 2 years ago, we know that carbon dioxide concentration will increase in the atmosphere. Now, with these turbines, what you are doing essentially, you are putting carbon dioxide pumps that will pump carbon dioxide in the ocean.
Yeah.
That means that you will fertilize the oceans in terms of algal growth. That means that you will acidify the oceans that will be detrimental to coral reefs. And as we talk today, I'm sure that you are aware of this filamentous algal growth in the Atlantic Ocean that spreads over 5,000 miles.
Yes, yes.
If that is in the proximity of these turbines, that will increase degassing of hydrogen sulfide in the air. So these are all the things, because the reason is you are not building one turbine, you will build hundreds of these turbines.
Yes.
And that will definitely, but is there any desire to investigate this? For working, if you don't mind, with universities like our university?
Sure. Yeah. So firstly, let me put it there. Well, we are very love to collaborate with you guys to explore some adjacent research area, like what you just described. So secondly, I want to share my 2 cents. The first is about the net carbon emission. Of course, if you purely look at this offshore turbine, it generates green energy, renewable energy. It also have some emission, right? In the end of the day, the matrix to measure here is not just about the emission the offshore wind turbine will generate. We call it like carbon intensity. So let me think about whether that's the right word. Basically, it factors in how much CO2 emission in order to generate how much of renewable energy. So you do that like a denominator and do that ratio and to prove as your matrix. But that's G internal matrix. We don't need to have everyone to buy in. So that's one of my point of view. Another point of view is there's some research topics talking about coexist offshore wind with green hydrogen production, with carbon removal. So when you kind of coexist, integrate these two together, you will generate some emission. Yes, you will emit some CO2. And in the meantime, maybe you produce more hydrogen that can offset the CO2 you produce. So there's different ways to offset that. But I'm not saying the offshore wind is really zero emission. Yeah. Even from the raw material perspective, you need a concrete, you need to have steel. All this material production will generate emission, will have emission, right? So, yeah.
No, I was thinking when you propose certain design for these turbines, if you are sorry, I'm not trying to be negative.
No,
if you are trying to think less about profit, and if you are trying to integrate environmental impact, for example, you can design these spatial distribution of the turbines that will minimize carbon dioxide flux at the air-water interface. Probably that will go negative in terms of how much you can produce electricity. But if you take that into overall equation, maybe that can be beneficial in the future.
Yeah, I think that will be a good conversation with BOEM for who launched this lease for offshore wind farm. Yeah, let them factor in this type of consideration. Yeah, everyone will follow. That's a very good suggestion.
Oh, sorry.
Interesting talk. So the O&M is more expensive offshore. You have to make these little boats. You do a lot of these optical techniques. You could also embed a lot more sensor technology in the blades or in the turbine mast. You know, there's lots of things that you wouldn't maybe not do on land because they're too expensive that maybe, you know, you could make, I'm sure it's possible to embed erosion sensors right in the blades. Would that be useful or is that already done?
It is useful, yes, yeah. So it could be one of the options. Like one of GE's competitor, they install the run sensor. I don't know how the run sensor works, but they can measure maybe the run drops, speed, that type of information. So they can control the turbine according to the run sensor data. So to avoid like the erosion. So I think there's a different options just for our method because in this generation of product, there's no rain erosion sensor yet, but we still want to do something, right? So let's figure out a software-based solution, no addition sensor needed. Yeah.
So there's some questions from online, so I'll go ahead and ask those. Our first is from Teja Desari, and they're asking, could you give a few examples for the 53 parameters that are output from the model?
So yeah, there's a lot. So firstly, the bending moments of the blade and the acceleration on the tower top. Of course, the generator speed, motor current. So there's a a long list. That's some example I can give. Yeah.
Cheesy He is asking, thanks for the great talk and introduction to the digital twin. Is the created digital model specific to one structure and geometry? Could you comment on how to transfer your DT model to other systems, like another wind turbine with different geometries, like different size? Does it require rebuilding the whole data set again?
Yes. So the simple answer is yes. As I mentioned, this is like a framework technology. Means we tell you, in order to do so, we need to involve 4 steps, and in each step, what you do, which kind of technology you can leverage. But it doesn't mean this is a solution for other components, other models, because very simple question. A very simple explanation is the high fidelity fixed model for data simulation here is for the blade design. If you want to work on transformer, it's a transformer model, right? You need to use a transformer physics model to simulate the data. So that's a simple answer. Please.
First thing, since I used to serve as a Coast Guard several years ago. So how do you consider the rare cases such as the hurricane or tornado? Because this is very rare and it impacts a lot into the wind turbine. But I think there's a few data samples to train your network, but their future impact will be very high.
Yes. So if we go back to this this slide, so you can see the blue dots are the kind of wind environment condition from the real field. If we're talking about a hurricane or tornado is on is on the land, hurricane, okay. So that may be somewhere over here, but this calibration method is specifically for this sites. If you're talking about the hurricane, which is some here, firstly, I'm not sure whether this type of calibration method will work. Maybe I will say no, because even for the turbine design perspective, in order to sail for the the Gulf of Mexico and Florida, those different sites, you need to have a different turbine. So the product itself will be different. So in that case, I'm saying even this yellow dots will be different because you're using different physics model to simulate the data. So for example, for GE, the 100x 12 megawatts, this is class 1B. For hurricane will be totally different class. So that's a new asset. So we can treat it as new assets. Yeah.
For your interesting talk. So I'm very curious about the first step about data generation. So I'm not familiar with how industry model works, but I just talk in terms of the CFD perspective. So usually when we prepare the data, so if you put more physics inside, more details inside, it will become more expensive. But the quality and accuracy is better. But if you want to make it rougher, and it will become cheaper, but you will lose accuracy. So I'm interested about your trade-off consideration for data preparation. So
oops, sorry. In this slide, we're talking about a 2 phases approach. The expense or computational power needs is in the first phase for data generation. Once you have that, you're done. And the model building is a purely machine learning approach. That's also why I said, okay, 11,000 of a DOE simulation, there's a 53 operation variable. And in the end, we did this kind of feature selection down to 7. Because you want to run this model in real time. In real time, it's a little bit exaggerated because the linear erosion does not change in minutes, right? It may change in week, in months. So, but again, in general, in order to run the model utilizing the real-time SCADA data, you want less computational power. You want the model to be very light. So that's why we reduce the inputs to kind of 7 to 10 variables. So once you split this model data generation and model building in two different phases, I think the concern you had may not exist.
Thank you for the talk. I was curious about the sensor boat that you described in the first part of the presentation. Is it continuously deployed? I understand it's remotely controlled. And then what makes it better than say, a flying drone? I know you mentioned that you don't have to stop the turbine operation while you're using the boat as opposed to drone. If you could comment on the benefits of using the boat design instead.
Yeah. So firstly, my point of view is not to get rid of drone inspection. Drone inspection is still very valuable, useful. We will use it for a very long time, maybe forever, for this type of maintenance. The project I presented is just another way to acquire data. So it's a complementary to the drone inspection. Yeah. Thank you.